First of all, I would like to thank the organizers, especially Professor Yoonjin Soo, for inviting me this nice conference. Thank you very much. Today's my talk is based on my joint work with Hiroyuki Tasaki from University of Tsukuba and Osamu Ikawa from Kyoto Institute of Technology. First, I will give introduction and I will mention some former our results, which I gave a talk the 15th and the 16th workshop. And next, I will give some definitions of basic notions. And then I will mention our recent result relating to fixed point sets of isometries of a Hermitian symmetric space of compact type. And then lastly, I will mention also our recent result about the intersection of two real forms in a Hermitian symmetric space of compact type, where we took a different approach to this problem from former our result. So I would like to start with a very simple example. Let's consider two sphere S2. And if we take any two distinct great circles, one great circle and another great circle, then they always intersect 2 points. In this case, here and here, which are antipodal. If at least one of these two circles is a small circle, it could be the intersection could be empty, like this small circle. There is no intersection. But if we take two great circles, they always intersect 2 points, which is antipodal. S2 is considered as CP1, which is a Hermitian symmetric space of compact type. And canonically embedded RP1 is a great circle in S2, and which is a real form in CP1. Real form is by definition the fixed point set of an involutive and holomorphic isometry. In general, we obtain the following theorem. Let M be a Hermitian symmetric space of compact type, and let L1 and L2 be real forms in M. If the intersection is discrete, then the intersection is an antipodal set. Here, an antipodal set is a subset on which the geodesic symmetry at each point acts trivially. I will give definition later again. We say L1 is congruent to L2 if L1 is transformed to L2 by an element in I0M. I0M denotes the identity component of the isometry group of M. If Hermitian symmetric space is the complex Grassmannian manifolds GKCN, which denotes k-dimensional subspaces in Cn. Any real forms is real Grassmannian GKRN, or if k is even, k and n is even, quaternion Grassmann GLHM, or if n is 2 times k, then unitary group. So in general, two real forms L1 and L2 are not necessarily congruent. But if they are congruent, we obtain the following. If two real forms L1 and L2 are congruent, and if the intersection is discrete, then the intersection is a great antipodal set of L1 and L2. Here, a great antipodal set is an antipodal set with maximal cardinality. The maximal cardinality of the antipodal set in a compact Riemannian symmetric space is called the 2 number, which denoted by sharp 2m. For a point O in a compact Riemannian symmetric space, each connected component of the fixed point set of the geodesic symmetry SO, the geodesic symmetry at O, is called a polar. I think it is not a relation with polar action. By making use of polars, we obtain the following. Let M be an irreducible Hermitian symmetric space of compact type, and let L1 and L2 be real forms in M. For simplicity, we assume the 2 number of L1 is less than or equal to the 2 number of L2. And we assume the intersection is discrete. Then the intersection is a great antipodal set of L1, except for the following one case. M is complex Grassmannian manifold G2M C4M, and real homes L1 is quaternion Grassmann GM H2M, and L2 is U2M. And in this exceptional case, we have the cardinality of the intersection is 2 to M, which is strictly less than the 2 number of L1, which is binomial 2MM, and which is less than the 2 number of L2. On the other hand, we have another approach to investigate the intersection of real forms. Let L1 be the fixed point set of tau 1. Tau 1 is involutive antiholomorphic isometry of M. Sorry, here is L2. L2 is F tau 2M. Then it is easy to see that the intersection of L1 and L2 is included in the fixed point set of tau 2 tau 1 inverse, where tau 2 tau 1 inverse is a holomorphic isometry of M, not necessarily involutive. If this fixed point set is discrete, of course the intersection is discrete. Moreover, if this fixed point set is antipodal, then the intersection is also antipodal. Conversely, if the intersection is discrete, is this fixed point set discrete? Or if the intersection of L1 and L2 is antipodal, is this fixed point set antipodal? We will refer to these problems in section 3. And next, it is known that a Hermitian symmetric space M of compact type is realized as an adjoint orbit of a compact semisimple Lie group G, like this, M equal add Gj in the Lie algebra of Gk, where J is an element in G satisfying this condition. By making use of this realization, we obtained a necessary and sufficient condition for the intersection of two real forms is discrete. And when the intersection is discrete, it is we found that it is an orbit of a certain Weyl group, which will be mentioned in section 4. So I will give some definitions of some basic notions. Let M be a compact Riemannian symmetric space. A subset S in M is called an antipodal set if For any points x and y in S, Sxy equal y. And the two number of M is defined by the maximal cardinality of antipodal sets in M. And the antipodal set is called great if it attains the cardinality of S is equal to the two number of M. These notions were introduced by Ban Chen and Tadashi Nagano. In general, great antipodal sets are not necessarily congruent to each other. But for symmetric R spaces, we have the following. Let M be a symmetric R space. Then any antipodal set is included in a great antipodal set. And any two great antipodal sets are congruent. I think it's a very good property. Here, symmetric R space is a compact Riemannian symmetric space which can be realized as a linear isotropy orbit of a Riemannian symmetric space of compact type. Especially a Hermitian symmetric space of compact type is a symmetric R space. For example, let's consider complex projective space CPN. Take a unitary basis of Cn plus 1, E1 to En plus 1, and take a point O with one-dimensional subspace spanned by E1. Then the geodesic symmetry at O is induced from the reflection, which is identity on this one-dimensional subspace and minus identity on orthogonal complements. Then we can see that one-dimensional subspace spanned by E1, E2 to En plus 1 is a great antipodal set of CPN, and the two number of CPN is N plus 1. Let M be a Hermitian symmetric space of compact type, and let tau be an involutive antiholomorphic isometry of M. Then the fixed point set F tau M is called a real home in M. It is known that a real home is connected and totally geodesic compact Lagrangian submanifold. A real home in a Hermitian symmetric space compact type is a symmetric R space and vice versa, which is proved by Takeuchi, Masaru Takeuchi. The classification of real homes in an irreducible Hermitian symmetric space of compact type was given by Lun and Takeuchi. As for the non-irreducible case, we have the following. A real form in Hermitian symmetric space M of compact type is a product of real forms in irreducible factors of M and diagonal real forms determined from irreducible factor of M. Here, a diagonal real form is defined as follows. Let tau be an anti-holomorphic isometry of M. Then this map xy to tau inverse y tau x is an involutive anti-holomorphic isometry of M times M. So this map determines the real form. The real form determined by this map is this d tau M, which is the pair of x and tau x, which is called the diagonal real form determined from M. And the existence of the intersection of two real forms follows the next proposition. Let M be a compact Kähler manifold with positive holomorphic sectional curvature. If L1 and L2 are totally geodesic compact Lagrangian submanifolds in M, then the intersection is not empty. So two real forms, the intersection of two real forms in compact Hermitian symmetric space of compact type is not empty. So now we consider canonical embedding of Hermitian symmetric space of compact type. It is known that Hermitian symmetric space M of compact type is realized as an adjoint orbit M equal add Gj in the real algebra of G, where G is connected compact semisimple Lie group, and G is the real algebra of G, and J is an element in the real algebra satisfies add J third power of add J equal minus add J. Let K be the isotropy subgroup at J. Then the real algebra of K of K is given by kernel at J. And let M be the image of at J. Then we have the orthogonal direct sum decomposition G equal K plus M. And at J is a complex structure of M, which can be identified with the tangent space of M at J, the point J. The action of G on M coincides with the action of the identity component of the isometry group of M on M. I0M is the identity component of the isometry group of M. Let AM denote the group of the all holomorphic isometries, and A0M denote the identity component of AM. Then we assume M is Hermitian symmetric of compact type, so it is known that I0M equals A0M. Moreover, if M is irreducible, IM mod AM is isomorphic to Z2. And AM is connected except for the cases, these two cases, complex hyperquadratic Q2MC and complex Grassmannian manifold GMC2M. In this case, AM mod A0M is isomorphic to Z2, which are result by Murakami and Takeuchi. The following result is known by Sanchez and formerly Sanchez, by Sanchez. Let M equal add GJ be a Hermitian symmetric space of compact type. Then a great antipodal set of M is represented as the intersection of M and T is a maximal abelian subalgebra of G. If an element G in G satisfies this, the dimension of the fixed point set of add G is equal to rank of G, and then small g is called a regular element. And recently we obtained the following result. Let M be a Hermitian symmetric space of compact type, and let G is an element in A0M. Then the fixed point set FGM is discrete if and only if G is a regular element. And if the fixed point set is discrete, this fixed point set is a great antipodal set. If we take a maximal abelian subalgebra T of K, which contains J, then since the rank of K and the rank of G is equal, so T is also a maximal abelian subalgebra of G. And by using root systems with respect to T, we have the following lemma. If G is an element in X, the image of exponential map of T, and G is a regular element, then G is a regular element if and only if the fixed point set of add G in G is coincides with T. Hence, if G is in X T, the fixed point set FGM is equal to the fixed point set F add G G intersection M, which is equal to T intersection M. And from the previous theorem, this we know this is a great antipodal set. This result we consider an element G in the identity component A0M. So next we consider the case where G is not in the identity component. So by the as mentioned before, we may consider only two cases, hyperquadric case and later I mentioned complex Grassmann case. Then now I will talk about complex hyperquadric case. Complex hyperquadric can be considered as the oriented Grassmann manifold G2R2M plus 2. Then AM minus A0M consists of is an element in orthogonal group O2M plus 2 with determinant minus 1. So if G is an element in here, then G is conjugate to this matrix, where R theta I denotes 2 times 2 matrix cosine theta I minus sine theta I, sine theta I, cosine theta I. Then we have the following. Let M be two-oriented Grassmann, and let G is an element in AM minus A0M. Then the fixed point set of G is discrete if and only if R theta I not equal to R theta J for any I and J with I not equal to J. And when the fixed point set of G is discrete, the fixed point set is an antipodal set, not great antipodal, just antipodal, with the cardinality is 2 times M, which is strictly less than the 2 number of two-oriented Grassmann G2 R2M plus 2, minus 2. This is a result for complex hyperquadric. And another one is complex Grassmannian manifold. But since we do not know AM minus A0M explicitly for GM-C2M, so in this case we can not solve it yet. When Hermitian symmetric space is complex Grassmannian GKCN, we obtain a refinement of theorem 3.2. This theorem. Let M be a GKCM, and let G is an element in unitary group UN. Then the fixed point set of G is discrete if and only if the multiplicity of each eigenvalue of G is 1. And the intersection of F tau M and F G tau G inverse M is discrete if and only if F G tau G inverse tau inverse M is discrete. These are F tau M and F G tau G inverse M is congruent to real forms in M. And this says that in the introduction I give this inclusion. This result says that if this intersection is discrete, this inclusion coincides equal. So lastly, I will mention about the intersection of two real forms in a Hermitian symmetric space of compact type. Let M be this is the canonical embedding of a Hermitian symmetric space of M of compact type. And let F tau M be a real form in M, which contains the element J. Tau is an involutive antiholomorphic isometry of M. Then tau induces involutive automorphism of G by this denoted by I tau, G to tau G tau inverse. Then the pair G and F I tau G is a compact symmetric pair. And the differential of I tau is an involutive automorphism of G. And we obtained the direct sum decomposition of G, G equal L plus P. L is plus one eigenspace of di tau, and P is minus one eigenspace of di tau. let K be the isotropy subgroup at J. Then, as I mentioned before, K is equal to the kernel of at J. And we said M is the image of at J. Then we have another direct sum decomposition of K equal K plus M. This is a canonical decomposition corresponding to this Hermitian symmetric space M. Then the origin J is included in the intersection of K and P. We choose a maximal abelian subspace R in P so that R contains J. And let R denote the restrict root system of this symmetric pair with respect to R. Now we investigate the intersection of a real form L and another real form GL for G in Lie group G. By the conjugation of maximal torus, we have the following decomposition: G equal F I tau G exp R F I tau G. So there exist B1 and B2 in F I tau G and A in exp R, such that G equal B1 A B2. Since L is the orbit of F I tau G through J, so the intersection of L and GL is equal to the intersection of L and B1A B2L, but B2L is equal to L, so this is equal to L and the intersection of L and B1AL, and L is also the orbit of F I tau G, so this is equal to B1, the intersection of L and AL. So it is enough to consider the case where G equal A. A is exp H for H in R, in order to investigate the intersection L and GL. Now here an element in the algebra R is called a regular if exp H is a regular element in G. So recently we have the following. The intersection of L and AL for A is exp H is discrete if and only if H is a regular element. If the intersection L and AL is discrete, the intersection is equal to the intersection of M and R, which is the orbit of WRJ. WR denotes the Weyl group of R. And this is a great antipodal set of L. this case is the case where two real forms are congruent. Sorry. So next, we consider the case where two real forms L1 and L2 are not congruent. Hereafter, we assume that Hermitian symmetric space of compact type is irreducible. We need irreducibility. Let Li equals F tau Im. This is real forms. As mentioned before, each tau I defines an involutive automorphism I tau I of G, and we obtain a compact symmetric pair G F I tau I G. And in this case, we have similar decomposition of G. G equal F I tau 1 G X sorry. I didn't introduce not yet, sorry. I will be appear later. And we have direct sum decomposition G equal Li plus Pi. And by the classification of by using classification of real forms, we may assume that tau 1 and tau 2 are commutative. Then we have direct sum decomposition G, the intersection L1 and L2, the intersection P1 and P2, and the intersection L1 and P2, L2 and P1. And we choose maximal abelian subspace R in P1 and P2. This is this R is maximal abelian in P1 and the intersection of P1 and P2. So under this situation, we obtain a symmetric triad, which is introduced by Ikawa. I don't want to give a precise definition of symmetric triad, but sigma is the restricted root system of L1, the intersection L1 and L2 plus P1, the intersection of P1 and P2 with respect to R. And W is a certain subset in R, invariant under minus identity. And sigma tilde is the sum of sigma and W, and which is an irreducible root system of R. Then we have the following. By using the theory of symmetric triad, we have the following. Let the intersection of L1 and AL2 is discrete if and only if H is a regular element. And if the intersection is discrete, the intersection is equal to the intersection of M and R, which is the orbit of Weyl group of sigma tilde, and which is also described as follows. R1 and R2 denotes the root system corresponding one to K equal L1 and plus P1 and L2 plus P2. This is a kind of refinement of a previous result, and by this result we also we obtain the theorem 1.3 again. 1.3. This one. Moreover, by using the classification of irreducible root systems, which means by case-by-case arguments, we can show that orbit of the Weyl group through J is two-point homogeneous. Consequently, a great antipodal set of an irreducible Hermitian symmetric space of compact type and the intersection of two real horns in an irreducible Hermitian symmetric space of compact type are two-point homogeneous. So lastly, I go back to the first example. Let M be a CP1 and L be a real RP1. Then, in this case, K is the real algebra of SU2, which is like this, and this is isomorphic to R3. And we choose J as this matrix. Then add J to third power is minus add J. Then the orbit of J add SU2 through J is SU2 over SU1 times U1, which is CP1. By this identification, this is S2 in R3. The unit sphere in R3. Now, let tau be a map which defined by x2 minus x bar for an element x in the real algebra SU2. Then tau fixes J, and tau preserves M. And the fixed point set of M is the fixed point set of tau in the real algebra SU2 and intersection M, which is like this, y equals 0. So this, and this is S1. And I tau is the map G to tau z tau inverse, which is equal to z bar. So the fixed point set of I tau in SU2 is equal to SO2. And we have the decomposition with respect to di tau, where L is this, which is the real algebra of SO2, and P is this. And we choose maximal abelian R in P, which is the spanned by J. In this case, it's one-dimensional. And we consider root alpha in an element R, then alpha is 4 times J, and the root system is plus minus alpha, which is the type A1, and while group is plus minus identity map. For H in R, if the inner product of alpha and H belongs to pi times Z, then S1 and add XH S1 coincides. And if the inner product alpha H is not belongs to pi times Z, then the intersection of S1 and add XH S1 is plus minus J, 2 point plus minus J, and which is the orbit of WR. So I finished my talk. Thank you very much.